you. Now I will share my screen with you. Just a minute. Okay. Yes, it's working. So, in the last class, we talk about some stress features. You remember the stress features are those morphological see in the surface of pads of aggregates, and they are formed by pressure and compression of the pads. They are common in clayey soils that has a lot of clay, and 2-to-1 clay minerals, so expansible minerals. And the soils can swim and swell, and because of that, these pads are compressed and form this shiny surface that are quite related to the pressure, and we call them sites. And these sites are these compressor features that we can see. Just okay. Today we will discuss about new morphological features. We are finishing these morphological features, but the texture, it's one of the most important of all. The texture is a measure that we made with our hands. We need to crush all the material and, oh, just a minute, someone's asking to enter. Just, oh, no, it's here. I'm sorry. Let's see. Why? The person stopped to ask, okay. Let me screen again. Share my screen. Okay. Share. Okay, it's working now. So to measure the texture of the soil, we need to crush all the material in our hands, and this material should be moist. So we need to have a lot of water, and we need to measure how much clay, sand, and silt this horizon, this sample has. So how clay rich or sand rich or silt rich is the sample? Okay, I'm feeling that this material has a clay texture or a loamy sandy texture, okay, because we can measure some material that has mix of a clay-rich horizon or a sand-rich horizon or a silt-rich horizon, and we can measure sometimes a loamic texture, a texture that we has a good proportion of clay, sand, and silt in the sample, okay? We have several soil texture classes, and all these texture classes, they should be classified according to the quantity, the measurement of the clay, the silt, and sand. So we have to measure the quantity of these particles, and after that, we can define, we can classify the texture class of each sample. The texture classes are very important because some diagnostic horizons, they could be present at any of these textural classes. How, as we can see, the spodic diagnostic horizon, okay, so the spodic horizon, it could be present, it could has any one of these textural classes. So we can have a spodic horizon with a clay texture or a loamic texture or a sandy texture is not a problem. So the spodic horizon could be identified in any of these textures or any other that we can see in this triangle. But we have some oh, just a minute. Let me be quickie. So maybe the person it's asking again. Okay. Okay. Oh, the person is not here. No, no. And let me ask again. Maybe it's working. Okay. But we have some diagnostic horizons that are not so permissive, like the vertic horizon, the vertic diagnostic horizon. We should have at least 30% of clay. So the vertical horizon could have a clayic texture or can be identified as sandy clay texture class or silty clay texture class or some of this sandy clay loam texture or this clay loam texture or this silty clay loam texture class. But we can't identify a vertical horizon with a loamy texture or sandy loamy texture or a sandy texture. It couldn't be identified here. So the texture, it's quite valuable to us to comprehend and classify easily the soil, the samples, and the horizons, okay? And the vertical and the ferhalic horizons, the ferhalic diagnostic horizon, it also has a minimal quantity, a minimal percentage of clay. It's 50%. So we can identify a ferhalic horizon with a sandy loam texture or sandy clay loam texture or a clay texture. All these textures here we can identify. Oh, just a minute. Okay. All these textures, all these texture classes, it could help to identify a ferhalic horizon. But these two, a sandy and a loamy sandy, it can help us to identify a ferhalic horizon. So we can't identify a horizon that has less than 50% of clay and more than 70% of sandy as a ferhalic horizon. It could be another thing, but no ferhalic horizon. So texture helps us a lot to classify horizons and layers properly according to the material, the quantity of clay, sand, and the silt and the material. Okay? And we can find some soils that has a high quantity, a high volume, a high percentage of coarse materials. And these coarse materials could be gravel, could be rocks, could be gravels, could be several materials that has a size, has a diameter higher, the diameter is higher than 2 millimeters. So they are particles that we classify as a coarse fraction of soil. And if the percentage of these materials is high, we have to include a new word in this textural class. For example, if we has less than 50% of coarse fraction, we don't need to change the texture class. So, for example, we just can identify a horizon as loan. So the texture class of a horizon, it's just loan or just clay or just clay loan or just silt, okay? But if you have between 50 and 35% of coarse fraction, you need to include a new word in a texture class. You should describe that horizon as a gravely, gravely, blah, blah, blah. For example, gravely lawn. So it's gravely clay, it's gravely clay lawn, it's gravely sand. It's not just clay anymore. You need to add this word, okay? If you have a percentage between 35 and 60%, you should include very gravely or very rock or something else. So you need to include this new word, and you can have a very gravely long class or a very gravely long texture class. It's just not anymore clay. If you have a lot of gravel, you will say very gravely wrong or very rocky lawn. Oh, I'm sorry. Very rocky lawn. You need to add this word very, and you need to add a new word about the coarse fraction. So we need to add a word about the coarse fraction. It's rocky, it's gravelly, it's grables. You need to add a word about the coarse fraction, the dominance of the coarse fraction, and you need to add this new word very to informate that we have a percentage of coarse fraction that's high. It's between 35 and 60%. If you have a quantity, a percentage of coarse fraction between 6 and 90%, you should use the word extremely. So extremely rocky lawn or extremely gravely lawn. You should use again a word to classify the coarse fraction, the dominance of coarse fraction in your horizon, and you should add a new word to include this information that we have a high percentage of these materials. And if you have less than 10% of fine earth and more than 90% of coarse fraction, you just need to use the word that describe the coarse fraction that horizon. So you just say gravel or rocky or pebbles. You should use the word that classify the coarse fraction dominance. You don't need to use a word to classify the fine fraction of that horizon. Okay? So again, if you has less than 50% of the coarse fraction, you just need to use these words, these classes, like loam, silt, clay, sand, only these words. If you have between 50 and 30%, you need to include a word about the coarse fraction dominance plus the fine fraction dominance. Oh, I'm sorry, just a moment. Asking, okay. Okay, so again, if you have between 50 and 35% of coarse fraction, you need to use a word to identify the coarse fraction dominance plus the fine fraction dominance. Something like gravelly lawn or rocky clay. It's not a problem. Okay? If you have between 35 and 60%, you include a new word here that's very. So you include very, the word that expresses the dominance of the coarse fraction, and the word that expresses the dominance of the fine fraction. Very, rocky, clay. Very, gravelly, lawn. Very, rocky, sand. It's not a problem. And you can change this word to very, to extremely, if the content of the coarse fraction is even higher. So we need to change very to extremely. Extremely, gravelly, lawn. Extremely, rocky, clay. Okay, and if you have more than 90% of the coarse fraction, you just need to use the word that expresses the coarse fraction. You don't need to use all this, just say gravel or rocky, the skeletal horizons or layers. The horizons and layers that has a lot of coarse fraction and a minimal quantity, a minimal percentage of fine fraction. Now we have to, oh, just a moment. Okay. Sorry. Here. Now we have to describe other features, are not properly soil features, but they include new information about soil and landscape, and that's quite important to us to describe this, and are properties that are related to soil formation factors. The soil formation factors are those components of the landscape that influence directly the soil formation. And we can say some words about them. We can describe the first one as a climate. So the temperature, the humidity, rainfall regime, evapotranspiration, precipitation, and several other properties that describe and that we can measure about climate. It's quite important and influence the soil formation. It's quite easy to understand that soils formed in periglacial or glacial conditions are very different from those formed in tropical, wet tropical, or dry tropical climate conditions. So climate is quite important to us to understand how soil is formed. And especially it's important because climate influence the watering, the leaching, and of course, the genesis of soils. Oh, I'm sorry, climate influence the watering and the leaching and the soil formation. Genesis. Now it's right. Okay. So it's quite easy to understand that if you have a lot of rain, if you have a wet climate, you have a lot of weathering and destruction of primary minerals as feldspars, pyroxene, olivine, and other primary minerals, and the formation of secondary minerals as goethite, hematite, kaolinite, gibbsite. And if you have a dry climate, you don't favor weathering, you don't favor the destruction of primary minerals, and you can find a soil with a lot of primary minerals, with a lot of feldspars, for example. And if you have a climate that you have a lot of rain, but evapotranspiration is higher than the rainfall regime, it's higher than the precipitation, you can concentrate salt in the soil and you can find gypsum, halite, and other minerals that is not usual to identify, but we can found in some areas. The climate, it's also quite important to understand how the soil is leached, how the infiltration and the movement of some bases, some nutrients like calcium, magnesium, potassium, sodium, and other elements, they leach in tropical and wet conditions in situations that they are higher than the sea level base, of course, but it's quite important to understand that the leaching is quite related to climate. So in a dry climate, you don't have a lot of leaching and you can form eutrophic soils that are very rich in nutrients. And this helps a lot the growing of the vegetation cover. Say thank you, the soil has a lot of nutrients and these nutrients are important to growing, to seeding of the materials. And of course, the climate, they influence also some pedogenetic process, some soil formation process that are important, that are related to variations of temperature, variations of humidity, and variation of energy in soil profile. Okay. We can describe also the relief as a new soil formation factor, and it's important to understand how relief induces or conduces the formation of soil, because relief is quite related to slope, declivity. So we can find some soils in very steep conditions like here, and the soil that are evaluating or formed here, the gravity potential is not so high. Oh, I'm sorry. Sorry about that. The gravity potential is not so high, so the erosion of these materials are not so high. But if you have a soil that evaluated here, you have a lot of declivity, the slope is high, and you have a lot of gravitational potential. So you usually suffer a lot of erosion, and it's common that this horizon start to be eroded and are deposited here. And you have a deposition of a lot of material. So relief induces erosion if you are higher than the sea level, and according to the declivity, the slope of an area, and the erosion, it comes back the rock, the parental material that could be in a B horizon, or even can renew the B horizon. And some of these materials could be now in the surface and can express another process that can't be expressed in a buried conditions, in subsurface conditions. So relief, it erodes the surface horizons and could help the formation of new horizons, or the formation of materials that are rich in primary minerals, because now these materials, they are in the surface, and the relief also can be burying some pre-existing soils, some soils that are formed in the past, and now they are buried, and we change a lot of process that start to conduce to soil formation here, because in a burial conditions you don't have a lot of oxygen, but you have a lot of pressure, so we can change the soil formation process here. Okay, it's quite easy to understand that soils are formed from the parent material. So rocks, sediments, and organic and inorganic, or classic and, oh, sorry, organic. All these materials, these two materials, they help to create, to form soils with specific soil properties. So if I have a rock soil formed from granite, probably they have some properties that are quite different from soils formed from sandstones, because these rocks are very different. These rocks are rich in quartz, and this rock has quartz too, but you have feldspars, you have biotite, and other minerals that could improve the natural fertility of these soils formed from granite in comparison compared from soils formed from sandstones. So of course it's quite easy to understand that these materials, they influence a lot the formation of soil. We can see that biological activity also influence the formation of soils. Trees and animals, the vegetables, vegetables and animals, they influence a lot the formation of soil, because they add organic carbon, they mix the materials, they include organic matter in the soil, and the organic carbon and organic material, it increases the absorption of some nutrients, and they increase the formation of pads, of some aggregates, because organic material and mineral materials, they generally have different charge. Organic matter are dominantly negatively charged, and the minerals, some of them has positive charge, so you can see the materials getting closer and forming pads and forming aggregates. The fine fractions start to create a horizon on a soil according to the activity of vegetables and animals. And especially the animals, they can mix the material, organic and mineral material from the horizons and layers, because they can dig some, they can dig and so they can mix and change the material from the position. They can transport some materials in the bottom horizon, in the deepest horizon, and carry on to the surface and mix all of these materials. And mixing these, they help the material to be renewed, refresh the soil properties, and also they can influence the uh, the case the gas chains in the soil, because they can improve the introduction of oxygen and subsurface horizons, and they also can improve the water permeability and the water conductivity and the soil. Okay, and at least we can identify in the end the influence of time in the soil formation. Time is quite important too, because all the interaction between these materials, between the soil formation factors, it depends on time. We need time to form soil, at least 1,000 of years to form some millimeters, 1 millimeter, 2 millimeter soil. Of course, depending on these conditions, the climate conditions, the relief, the parent material, and the living organisms that act in the soil. But time is quite important to form this soil, because all these interactions, all the processes that are formed by these interactions, these take time. So they need time to create soil, to create horizons. Okay? Oh, someone asked something, just a minute. Okay. Lidima, please.
Okay. JJ, I have a question. All these soil formation factors, can they work in isolation? Must all be present, like the actions of the climate, the relief, the parent material, the biological activities, and before a soil can be formed? Is it possible for a particular soil to be formed with only effects of climate, or must all the factors be involved before a soil is formed? Did you get me?
No, can you repeat me, please? Can you repeat your question?
My question is, all these factors of soil formation, must they be present before a soil is formed? Can climate, for instance, no, climate involves rainfall, temperature, humidity, can it act on isolation in absence of others, or must they all be present before a soil is formed? Did you get me?
No, I understand. Okay. Yes. You have to have all these conditions, all the soil formation factors acting to create a soil that's result from those interactions. So we need to have at least 1,000 of years of wet and tropical climate to form just few millimeters of a soil that has properties that we can understand that this soil was forming according to these climate conditions, or this soil was formed according to these relief conditions, the topographic conditions. So we need that they all acting at the same time to form just a few millimeters, but we need to have all these materials acting at the same time. We can see some soils that are formed in the past, like in a course, the paleopedology course that we are taking on, and they have specific soil properties that are related to different time or different climate conditions, but or different parent materials. They could be related to the burial materials also, but we need to understand that soils are formed by the interaction of all these soil formation factors, and they should present specific properties. They should present specific characteristics or specific behavior to create a soil that represents, that are formed by these behaviors, by these properties. Okay? Okay? I will share with you some references about the timing of the soil formation and how can we see if you change a little bit one of the soil formation, like if I change only the parent material, or if I change the relief, or if I change the climate, or if I change time, how soils are quite different because they are formed by the interaction of all the soil formation factors. Okay. Okay. So let's discuss some of these properties about the soil formation factors that are important to describe when we are describing a soil in the field. Okay. And let's start with climate conditions. And climate, it's quite important. We discussed about that in the last slide, because it influenced the weathering, it influenced the leaching, and some soil process, okay? So process formation. And we need to measure the soil temperature. That's not the same of air temperature, okay? The soil temperature, they usually are measured in a surface like 5 centimeters, and in the subsurface 50 centimeters. Okay, and usually the soil temperature, it's different from the air temperature depending on the humidity, depending on the quantity of solar energy that you receive in the landscape, and depending on the soil cover, you can present different soil temperatures. Okay, the soil temperature is described, it's classified in 1, 2, 3, 4, 5, 6 classes, 6 different classes. Okay, we have the geolic, cryic, frigid, they are the coldest, the mesic, thermic, and hyperthermic, that they are harvest soil temperature classes. Okay. Here.
Can you share
Okay.
your screen?
Oh, I think that I'm sharing. Just wait. Oh, I'm sorry.
Sure.
I'm sorry. I forgot to share. Sorry. Okay. Okay. Now I'm sharing again. Let me show you all here. Oh, okay. As I said, we need to measure the soil temperature, okay? And we usually measure at 5 centimeters and 50 centimeters. And it's quite different from the air temperature because the air temperature has a different density and the gas mix very easily, and the soil temperature, the gas phase is not so easily to mix, and we have a lot of solid particles and some liquid particles too that increase the temperature. Okay, and we have the six classes, soil temperature classes. Okay, the Jalek, Krajek, and Frejek, they are the coolest. Mesic, thermic, and hyperthermic, the warmest soil classes. Okay. Here is just an article that you can find here. I can share this reference with you all too. That's about the soil temperature in the majority of countries and the continents in the world, except from Antarctica and Arctic. Okay, so we can see here the annual mean temperature, and here we can see that we have a lot of high temperatures in South America. That's quite close to Africa and the Middle East and Australia too, India too, and we can see very easily here as we have some low temperatures here in the high latitude, and here we can see some low temperatures because the highlands that we formed here. Okay, so it's quite important to understand that we have different temperatures, and this is just an annual mean temperature. We can see here some change of these variables of the temperature according to the summer or winter and the rainfall season or the dry season. We believe that temperature change, and here we can see that these temperatures are changing according all of these properties. Of course, some soils, they change easier than other ones according to the clay content, the sand content, the minerals that we can find in soil, the content of organic matter, the land used, the soil cover, and the type of the organic matter, the quantity of water, the relief, the position in a topography situation. We can find a lot of variables that change, that influence the soil temperature. The first one, the first class is the Jalek, and Jalek is present in materials that has low temperatures, so low temperatures, and you have a mean annual temperature that's below 0 Celsius degree, or you have a mean or average annual temperature that's below 1 Celsius degree at 50 centimeters depth, or at a densec, lithic, or paralithic contact. Okay, and of course, if you have some water in the soil, because the low temperatures, we can find ice in the subsurface or even in the surface horizon. Okay, because you have a lot of low temperatures in a year. Okay, and the average, the mean annual temperature, it's very low. We can also discriminate this class in hypergelic, pergelic, and subgelic according to the temperature. If you have temperature below minus 10 Celsius degree, you are a hypergelic soil. If you have between -4 and 10 Celsius degree, minus 10 Celsius degree, you have a pergelic soil temperature regime. And if you have more than 4 to, oh, I'm sorry, it's just -1 Celsius degree to -4 Celsius degree, you have a subgeotic soil class, soil temperature class, soil temperature regime. So we can identify these materials if you have a lower temperature than just 1 or 0 Celsius degree. They are common on Russia, they are common in Antarctica and Arctic, of course, because the low temperatures there. We also can identify the cryotic soil temperature class that's related to temperatures that are higher than the geolic regime. So we can see some temperatures that between 0 Celsius degree and 8 Celsius degree. Okay, and if you and you can find permafrost. Permafrost are on horizon or a layer that has temperatures below 0 Celsius degree for at least 2 consecutive years. So the cryotic regime, you can't identify a layer or horizon that has temperatures below 0 Celsius degree for at least 2 consecutive years. Okay, if you found the situation, you have the geolic soil class. But if you have temperatures that vary between 0 and 8 Celsius degree, and you don't have a permafrost, a frozen soil, a frozen horizon, you can have a cryotic regime, a cryotic class. Okay. If you have mineral soils, soils that you don't have a lot of organic matter, and if you are not saturated, you are not flooded soils in the summer, but they have an O horizon, they should present a temperature between 0 and 15 Celsius degree. And if you don't have an O horizon, the temperatures should be between 0 and 8 Celsius degree. Okay, like this one, we can see a mineral horizon, a mineral soil, I'm sorry, and we can see that they are flooded. So of course the temperature at 50 centimeters should be between 0 and 15 Celsius degree. This figure, it's quite important. It's quite interesting to us because we can see some of the processes that act in cryotic and geolic soils. If you want to define, to separate, to identify the horizons, we can see here the surface, and we can see here a first horizon. We can see here another horizon, and if you see very careful, you can see a horizon here, something like this. Okay, because we have this dark material and we have this grayish material, and this kind of ascending material, this upper horizon, this irregular boundary between the horizons, it's typical to cryotic regimes that you have very different temperatures in the surface and the subsurface. And if you have lower temperatures in the surface, the material, if have a lot of water, you can see that the clay starts to migrate from the subsurface horizon to the surface horizon. Okay, it's quite common. We discuss about the soil process in the next classes, and it's quite common to identify this kind of process in this regime, the cryotic regime. Okay. If the soil is saturated, it's fluid, and you have a lot of water, the temperatures should be between 0 and 13 Celsius degree if you don't have an O horizon, or between 0 and 6 Celsius degree if you have a high stochastic pattern or a O horizon, sorry. Something like this. You can see the W layer, a lot of water here, and this soil has a lower temperature between 6 Celsius degree, and we can identify then as a cryotic soil or cryotic regime or cryotic class. Okay, if you have an organic soil or soil with a lot of organic materials, organic carbon, the temperatures should be between 0 and 6 Celsius degree. Okay. For this, you just need to measure the temperature in the surface and the subsurface horizon. Just that. We can also identify the frigid texture, or the frigid class, I'm sorry. The frigid class are related with a temperature between 0 and 8 Celsius degree. That's quite similar to cryotic regime, but you have a warmer summer than cryotic class, okay? So we have a difference between the mean summer temperature and the mean winter temperature. It's higher than 6 Celsius degree. Of course, mean summer soil temperature and mean winter soil temperature, okay? So we have a summer that has higher temperatures than the winter, and a lot of very higher temperatures than the winter, and the difference between them is high. It's higher than 6 Celsius degree, but you have a soil that has a variation of temperature, annual temperature, average temperature between 0 and 8 Celsius degree. Something like this in some temperate regions like Europe and Russia and United States. We can also identify the Mesic regime. And the Mesic regime, we have temperatures between 8 and 15 Celsius degree. And the difference between mean summer soil temperature and mean winter soil temperature should be higher than 6 Celsius degree. So you have a summer with higher temperatures than the winter, of course, but they are very higher than the winter, so the difference is higher than 6 Celsius degree. You can find some soils like this. We also can identify the thermic and the thermic soil temperature regime. The thermic soil class is related to temperatures of the subsurface that varies between 15 and 22 Celsius degree. Okay, and again, we have a summer temperature that's quite higher than the mean winter soil temperature, and the difference between them, it's equal or higher than 6 Celsius degree. You can see some wet and tropical soils like this one. And we can identify the hyperthermic soil temperature regime or hyperthermic soil class is related to soils that has temperatures than higher or equal to 22 Celsius degree. And again, the mean summer soil temperature, it's higher than the mean winter soil temperature. And this difference, it's equal or higher than 6 Celsius degree. And the hyperthermic, it's very useful to identify in semi-arid and arid conditions. Of course, in hot, semi-arid and arid conditions, because we can find some cold deserts too in Antarctica, for example. So if you have a hot and semi-arid or arid condition, probably you have a hyperthermic regime, hyperthermic class, okay? And beyond the temperature, we should also describe the quantity of water in the soil moisture, and the soil moisture regime is quite related to metric soil potential. So we describe the quantity of water in surface because we need to know how much water we have in the soil, how many months or how much time the vegetables and animals start to suffer because the dryness of the soil, okay? And we usually measure this using these rings, these volumetric rings that we add in the soil, and we sample these materials like this one to preserve the structure, the initial structure of the soil. So we don't want to mix the horizons of the particles because we want to preserve the structure, the voids, the aggregates, the pads in this sample. And we usually bring these samples to lab and measure the quantity or how much water is stored in the samples, okay? We can use this material, the Richard chamber, that measure the quantity of water in different metric potentials. So we can measure the quantity of water, and we can calculate some parameters, some properties of soil that are related to water. We can calculate the total porosity, the total quantity of voids that's measured in a tension equal to 0. We can measure the field capacity, that we can measure this in a tension that variate between minus 10 and minus 1030 kilopascal. And we can measure the whiting point. That's the condition that we don't have a lot of water, and we measure then in a tension that is equal to minus 1,500 of tension, okay? The total porosity, they tell us the quantity of voids that we have in soil and how much water this soil can storage. So when you have higher total porosity, you have a higher capacity of storage water, or of course case in the soil. And someone asked me something, just a minute, okay? just open here. Oh, Nidima, please.
David, is it this soil water? Is there any, as in, is it possible for the water content of horizon A to be different from horizon B? Or the soil sample measured, is it collected at a particular depth? Did you get me?
Yes, actually, yes. Actually, it's very common that the surface and the subsurface horizons, they present very different water quantities of water, okay? Because they have different properties, like the A horizon or the E horizon, they generally have a lot of sand, and some B horizons, they don't have a lot of sand, like the Vortic, the Argic, or the Ferhalic horizon. They don't have a lot of sand, and they have a lot of voids. But the A horizon, they generally have a lot of sand and they have a lot of voids, but they have larger voids that couldn't keep the water in the surface horizon. Like they are so big that they can keep the water in the horizon. Only the microporosity, the minor voids, they can keep the water inside the void against the gravity and keep the horizon wet, okay? But the larger voids, they can't keep water storage in a horizon because gravity acts on high and larger voids, and they generally lose the water because gravity start to to act in these voids, and water start to migrate from the surface horizons to the subsurface horizon. Okay, so we will discuss this in the next classes, but it's quite common to see some soils that has different quantity of waters and quantity of temperatures in the surface and in the subsurface horizon. Okay. Uh, Kenneth asked me something. Just how would you describe soil temperature variations? Oh, Kenneth, we need to measure, okay, with some sensors that we should install in the soil, in the surface and subsurface, and the temperature keeps being measured all the time. Okay, we have some equipment specifically for this that measure temperature. Like you can measure your temperature with a thermometer, and we can measure the temperature of soil with a thermometer too. Okay, it's basically the same, but we need to measure the temperature of soil like between 20 minutes or 1 hour or one day, and we need to measure the temperature a long time through a year or 2 years consecutive. Okay. Fine. Okay. Okay.
Okay.
Mhm. So the total porosity is the total quantity of water that could be storage and soil, and which higher is the total porosity, higher is the quantity of water that soil can storage. Okay. Of course, some soils that was affected by mines, they decrease the total porosity, including some soils that was affected by animals, by pasture. They usually decrease the total porosity, and they could decrease a lot, and a high difference of pristine soil and non-affected soil and anthropic affected soil. The field capacity, it's the quantity of water that the soil can storage against the gravity. So here is the total quantity of water that's storage, and here is the quantity of water that's storage against gravity. So it's raining right now, and all voids of soil is fulfilled by water, and I can comprehend that the total porosity was achieved, that all the quantity of water that soil can storage is achieved, okay? And now stop at the rain, and the gravity start to act on the particles, especially in the water, and that water that are in the higher voids like this one, the water start to move from this horizon, this surface's horizon, to the subsurface's horizon, or to the rock, or to tidal level, okay? The water start to move because gravity start to act in the soil after the raining situation, the raining event, and water start to move. And that water that was storage in this little voids, this water is not affected by gravity. So this water still storage in soil, in horizon. So the fuel capacity is the quantity of water that's storage against the gravity in this little voids, not the large ones, because the large ones will lose water. Okay? And of course, how much higher is the field capacity? It's better to vegetation cover, because this quantity of water, it's those water that could be useful by vegetation. If you have a high total porosity but a low field capacity, probably your soil has a semi-arid condition or a semi-arid kind of vegetation, okay, or a savanna or a dry forest, because you don't have a lot of water to to be evaluated to vegetation cover. And all water that is inside the soil is just migrates from the surface to the subsurface horizons, okay? And the last one is the whiting point, and the whiting point, it's a very low tension that's related to the water that's also storage in this very thin voids, but those volumes, those percentages of water that is so strongly related to solid phase that plants can't access. So the whiting point is the water that plants can't access. They can't use this water. And of course, if I have a high wilting point, it's not good to vegetation cover because soil, the mineral phase, the solid phase, has a very high capacity to absorb water, and it don't release to vegetation. Okay, and I need to compare all these values. We can just make a very quick example here. Like I can measure soil like this one, that we have a lot of voids here. All these white regions are voids, okay? This is not one, this is a quartz grain, okay? So here are voids. And I can measure my porosity, and it achieves fifth or half of the soil just voids, okay? So half of my horizon or of my soil could storage water. But when gravity acts and moves the water that are storage in this huge voids, I just can storage something like 35%. So I lost 15% of water just by moving. Water that moves from the surface horizon to the subsurface horizon, okay? 50% of water I lost just by moving, my migration between horizons, okay? And if I measure my wilting point, I can identify that I have a wilting point of 25%. So if I have a quantity of water that's equal or less than 25% of water in the soil didn't release water for vegetation cover. Vegetation cover couldn't access this water, okay? So I have a specific condition that I just can use 10% of the water that's storage in the soil. It's not so much. Actually, it's very, very few quantity of water, because the soil just storage 35%. But if the soil has just a quantity of 25%, they stop it to release water, okay? And I can present another example, like I can present now a soil with just 40% of total porosity, so it's lower than the before, the first example. So the storage of water is lower compared to the first example. The field capacity is 13%, so I lost here just 20% of water that moves, that migrates from the surface horizon to the subsurface horizon, okay? And I can measure a whiting point of just 15, or at least lower. And now I have 15% of water that it's useful to vegetation cover, okay? I can measure and identified that this soil, the second soil, has a higher quantity of water that's useful, that's available for the vegetation cover. It's higher than the first example that we have just 10%. So we can compare this data and understand why we can find some dry forests in an areas and why we can find rain forest in a dry area, the context, a dry area landscape. It's because soil storage water, and the water that's storage in soil, it's more important than the precipitation, the rainfall, because the water in the soil, it's what the vegetation access. It's not the precipitation, okay? And of course, we can see some change in vegetation cover according to the total porosity, field capacity, and the whiting point, okay? Everyone understand these questions, these concepts, these definitions are very important to us.
It's okay with me.
Oh,
I'm okay
okay.
with it.
Okay. Very good. Very good. And now let's see some classes of soil moisture. Okay. We have the equic and the perequic, the eodic and the periodic, the eustic, cheric, aretic, and toric. These ones are the hottest, and these ones, oh, hottest and driest, I'm sorry, driest and hottest. And these ones is the wettest. We have more water here in the equic, perequic, eodic, and periodic, and we have less water in the cheric, aretic, and toric, especially in the aretic and toric soil classes. Okay. This is an example of equic soil class. The equic soil class is identified in soils that are saturated by water. So the oxygen is virtually free. We can't find oxygen here because we have a lot of water, and roots and microbiotes and other animals, they consume the oxygen, and the soil start to get gray like this one. And we can also see some models here, is not a problem, but this help us to understand that this soil has a equic condition, condition that we have a lot of water that's saturated, and oxygen it's virtually free because all the iron have been reducing by biological activity. This gray color help us to understand also that this soil it's above biological 0 point. This marks the biological activity. This gray color is formed by activity of organisms like roots and animals that consume oxygen and produce organic matter that to be mineralized, to be destroyed by the microbiological activity, should reduce iron. So iron 3 is red set to iron 2, and we can see this gray color. So the destruction of organic matter produced by biological activity, it act to reduce iron 3 to iron 2 and comprehends and create this gray color. and this gray color is related to aquatic regime, the aquatic class. Okay? If we have some landscapes that present a long-term regime of aquatic conditions, of saturated conditions, we have a per-aquatic. So we can find some soils that seasonally are flooded, but they are not flooded all the time. And we can see some soils that are flooded all the year, all the time, and so they are per-aquatic. They have a per-aquatic condition, a per-aquatic class. Okay? So it's very easy to identify this kind of soil classes because they are related to a high quantity of water and soils that are not, doesn't have a free drainage. They are not well oxidized by oxygen and iron. It's another picture. We can see easily, very easily here, water, okay, and a lot of organic matter accumulated here because we have a lot of water. We also can see the aeric or toric regimes. They are the same, but for some classes, we use this word, and to another soil groups, we use this word. So they are the same. We just need to note that sometimes you use aeric and sometimes you use toric. When we should use each other, JJ, I will teach you in the next classes how to choose the better word, okay? But they are the same. It's not a big problem to solve this. And the soils that are dry for more than half of cumulative days per year, when soil temperature and at F depth of 50 centimeters, it's above 5 Celsius degree. So they are hot and dry soils. Okay? If I see this, they are dry for most than half of cumulative days. If I have a year with 365 days, I know that I have at least 182 days that this soil is dry. So I don't have a lot of water here. They are very common regimes in arid conditions, in desert conditions, okay? And it's quite important to highlight that aeric and toric conditions classes are different from anhydrous conditions. The anhydrous conditions are conditions of you have a dry condition, but a cold one condition, like in Antarctica or Arctic conditions, okay, regions. We found a dry area, but it's not a hot area. It's a dry and cold. It's different from the aeric and toric that's dry and hot. Okay? So, some deserts and some soils, very sandy soils that has a lot of sandy and a very few contribution of organic matter to form dark horizons because we don't have a lot of biological activity in these areas, okay? We can also see the eodic and the per-eodic conditions. The eodic and per-eodic soil classes are related to soils that are not dry for at least 90 cumulative days, but the precipitation is higher than evapotranspiration, or the rainfall is well distributed in the year, and the soils are not saturated. So the euthic is different from the equic, because in equic we have a lot of precipitation. The precipitation is higher than evapotranspiration, and we have saturated soils. In euthic conditions, we don't have saturated soils. We have soils that we can find in rainforests. So we have a lot of water, but the soil is well drained. The water is not stopped in the soil, and the soil doesn't present and doesn't show a gray color, but I can see a red or usually a yellow color to understand that this environment that has a lot of water but is not a non-saturated soil. It's not a saturated soil. It's not a poorly drained soil. Okay? We also can understand how some areas has a eustic regime that's intermediate particular regime for some semi-arid regions and the majority of temperate regions that has temperatures between temperature not that has a humid a moisture regime, sorry, a moisture regime between the aeritic and the aquatic conditions. So they are in the middle of this moisture regions, okay? And we can found in semi-arid regions like this one, then some of the soils. We can present the Charic, and the Charic, it's specifically to Mediterranean region. So we can found some soils here, and here, and here, and here, that has the Mediterranean climate, that has a summer that's dry and a winter that you have a lot of rainfall. So it's the opposite of the majority of climates. And in these areas, we can find soils like this one. They are not so developed, they're not so leached soils, but that present a lot of organic carbon because we have a quantity of water that helps the vegetation curve to be dense. Okay. Has anyone has any question? Do you understand how to describe the soil moisture and the soil temperature regimes, soil temperature classes? Anyone?
I'm okay.
Okay, Nedima?
I'm okay. I'm okay.
Okay, okay. So I will stop now. And in the next class, we will start to describe some soil relief conditions that we should describe to better understand how soil is in a landscape, okay? And with the next class, we will finish the soil description, and we will start to classify soil according to the soil taxonomy and the World Reference Base for Soil Resources. So I ask you to finish the reading of this material, this reference, so we could start in the next week. We could start in next week a new topic of our classes. Okay?
Okay.
Okay, okay. So thank you so much, and I see you. Bye-bye.
Okay,
Bye.
okay, JJ. Thank you.
Bye-bye.
Thank you, JJ.
Thank you.
You are welcome.